Hi all, this is Mr. Yeager for chemistry. We are continuing our equilibrium unit and getting to the equations, which basically this is the second half of the unit really, and so we're going to be done after this part. So we already talked about equilibrium where this is occurring when the rates of reaction are going back and forth between the reactants and products equally. That doesn't mean that we have equal amounts of products and reactants, and that's what we're going to really see in some of these equilibrium equations today. We talked about Le Chatelier's principle and how if we manipulate the concentration, the temperature, the pressure, those are all factors that can manipulate what might happen to the reaction where you knock it out of equilibrium and it's going to try to adjust to get back to equilibrium. All right? So there's a little bit of that piece that we're going to kind of see some today as well with these equations. So what we basically have is we're going to the calculations. I'm going to jump right into it and go, here's the equilibrium equation. So we have a chemical reaction. Let's say we have 2A aqueous reacts with B gas, which is at equilibrium with 3C, which is a solid, plus 2D aqueous. Real quick, just to make sure we're really clear about this, the whole idea is A, B, C, D are different compounds. By putting the coefficients 2, 3, and 2, 2, 1, 3, 2, if I read them in order, this reaction is balanced. All right, I'm just using it to help us set up how we use the equation because those coefficients, again, are going to be something that's important in the end. So we do have to have a balanced chemical reaction. We also have to pay attention to the states of matter in that chemical equation. So based on this reaction, the chemical equation you can see will be K. K is known as the equilibrium constant. You might see it written as KEQ. Okay, you might see this, or KC, all right? Sometimes we write it those ways just to say that they're at equilibrium, all right? K is fine as well. But based on the reaction above, K will equal the concentration of D squared. So I'd square the concentration of D. Again, when I put a chemical into brackets, this is representing the concentration of it. This can be concentration or pressure. Those are the two things we're going to be looking for, is concentration or pressure are the two that we could use. We'll primarily use concentration. But it would be D squared divided by A squared times B. So it would be the compound D, its concentration squared, divided by the concentration of A squared times the concentration of B, no square. All right. You can also see that C, the compound C, is not in this reaction. So what are we seeing here? Okay, we kind of go hit the different parts. What we've done is the products are going to go in the numerator. We're going to basically, you multiply the products in the numerator together. All right. But again, we didn't put all the products. We only put D in there. So why is C not in there? We'll come back to that. But products are going to be in the numerator, multiplied. And then the reactants are going to be in the denominator, multiplied. Then what we do is the coefficient from the chemical reaction, all right, is the exponent that you're going to raise the concentration to. So going back up again to it, D is squared because there's a 2 coefficient in front of it. A is squared because there's a 2 coefficient in front of it. B is just to the first power because there's only a 1 coefficient in front of it. If I was going to use C, what should I see happen? It should be the concentration of C cubed times D squared over A squared plus B, or A squared times B. Okay? The thing is, again, let's make sure about this. The coefficients will become the exponent that we have to raise your concentration to in the reaction. All right? But again, why is C not in it? Solids are ignored. Okay? We do not pay attention to solids and liquids. We mentioned that last video in the first part of this, where solids and liquids are not going to really manipulate the equilibrium because we can't necessarily change them at all. They are there, and they're going to have that consistent, constant concentration, essentially. It could change ever so slightly, that's usually what we say is, will it change some? Yes, but it's so minute in terms of what happens to it that we can essentially ignore, and it doesn't play a role in the equilibrium constant calculation in affecting the overall equilibrium of the system either. Okay, so we ignore solids or liquids. There will be a couple of problems where you might see, you know, like something like HCl aqueous plus H2O liquid. H2O liquid will not be in the equilibrium equation. Okay, so liquids and solids are ignored. So we basically the only ones we need to pay attention to are aqueous and gases. All right, aqueous and gases is what we're looking at with it. All right, and basically we will only be focusing really on the aqueous ones because we have to have all of the values in molarity. We have to have the concentration of them in molarity is what we're looking at there. There is a way to do it with gases where you do it all in kilopascals or a pressure unit. We're not going to really deal with that too much, all right, is what we're looking at in this particular case. Okay, so that's basically it. So again, products are in the numerator, raised to their coefficient. Reactants are in the denominator, raised to their coefficient, and we just simply divide. This K value, be very prepared, it can be very large or very small, okay? There can be K values where you're at 1,000 and people are going to be like, is that okay? Yes. You're going to have K values where it's times 10 to the -5th, -6th, and so forth. So you cannot really be sitting there going, am I right because of what the number is? We have to sit there and go, am I right because I am doing the math right and I've set this up correctly? Okay. So K values. All right, and I have that down there. What is K in the end? What does K mean? Okay. K is standing for the equilibrium constant. All right, and it is for a particular temperature. So the same reaction could have multiple equilibrium constants if I keep changing the temperature. All right, but that's why you'll see when we do some of the problems, it'll say at a constant temperature, at this temperature. We can kind of ignore it. We just need to know that, hey, the temperature's not changing. Okay, but the equilibrium constant is going to be helpful for us to figure out the concentrations of solutions or gases in the chemical reaction itself. Okay, so we can figure that out. And like I said, it can be large or small, so don't worry about that. So we're going to come back to that in a second and start calculating it. There's also another letter, Q. Okay, Q is known as the reaction quotient. The reaction quotient. It is solved the exact same way as K, but so this is going to be products over reactants raised to their coefficient. All right, but what the reaction quotient is this is that we consider the current state of the reaction. So it may or may not be in equilibrium. You're going to see problems in a moment where it'll say, it'll say you are given this much stuff, reactants and products, find the reaction quotient. Here's the equilibrium constant. Does it match the equilibrium constant? Based on what the equilibrium constant is, what's going to happen to the reaction? All right. So the reaction quotient is just saying where are we at this point. It doesn't necessarily say we're in equilibrium. So K and Q, though, are very much related. Okay. We use both of them to figure out which way the reaction will go to get to equilibrium. All right, based on what the K value is and the Q value. So you might not have to solve anything, and I'll just say, here's K and Q, what's the reaction going to do? Is it going to move toward the products? Is it going to move toward the reactants? Is it at equilibrium? So here's your basic scenarios. If Q is equal to K, you're at equilibrium. That means somehow you added it perfectly. You added all the reactants and all the products just perfectly. And they are reacting, they're going back and forth, they are going toward the reverse reaction and the forward reaction, but they're going at an equal rate, all right? It's already at a state where it's happy. If Q is larger than K, if you come out that Q is larger than the K value, the reaction will shift toward the reactants. That's because the numerator is too large, all right? The numerator of this particular reaction is too large. You have too much products. The numerator, again, is the products. So, again, if you have a large Q, that means we have a large numerator at the top, just to reiterate, over the denominator, compared to what I have in the K value, okay, compared to what K is. So essentially what I'm doing is I need to lower the Q value. Well, the way to lower the Q value is to lower the amount of numerator and essentially increase the denominator. So in other words, reduce the amount of products, which guess what, will produce more reactants. So if Q is larger than K, you will shift toward the reactants always. Now you could try to just learn this as just remember that, because then if the opposite is true, the reaction will shift toward the products. You need to increase the numerator. Your K value, your Q value is too small compared to the K. We need to increase that up to where K is until they're both equal in the end. All right? So that's where we're looking at with the two values here. And again, we'll be doing some problems in just a moment with it. We're actually going to do it right now. Okay? So let's look at a couple problems right here. All right, so you can see my chemical reaction right here. All right, let's just practice figuring out this. So it says calculate KEQ for the reaction if the equilibrium concentrations are SO2 is 0.42 molar, O2 is 0.21 molar, SO3 is 0.072 molar. So key here, it already says it's at equilibrium. Okay, so we're not solving for Q, we could just solve for K. We do have all of the concentrations, and then I want to look down here, we have gas, gas, and gas. So that means everything will be in my reaction here. All right, everything will be in my equation. The only issue though is we need to make sure it's balanced. This is not balanced yet. I have one S, 3 O's, but 4 O's. So I need to increase the number of S's, well, O's, but that increases the number of S's. So I have 2 S's, 2 S's, 6 O's, 4 plus 2 is 6 O's. So now what would be my equilibrium equation? That could be simply the question. My equilibrium equation would be the concentration of SO2 squared times the concentration of O2, not squared because there's only a 1, divided by SO3 squared. So then I can plug everything on in to that. But there I hope you see what we're doing here. I have my products on top raised to the power of their coefficient over the reactants on the bottom. All of them are included because I have no solids or liquids. So this would be SO2 is 0.42 squared times O2 0.21 divided by 0.072. And since this is in molarity, I mean basically everything does essentially cancel, squared. Squared in the end there. There we go. Okay. Basically KQ is just, we don't have any units at the end with it, okay, at all. Even though it looks like you might have like a molarity left over, there are no units in the end. The M's just basically cancel themselves out. All right. So I would go ahead and do 0.42 squared times 0.21. Sorry, doing it right now. Divided by 0.072 squared. Okay. And I think we're all good, right? Yep. So the KEQ for this one would simply be 7.1. And there's your answer. 7.1. All right. Now, there is actually one thing I just thought about with this that I did not mention. Okay. With the KQ, you can tell which side is favored based on the size of the K value. You can tell which one is favored. All right. Because the K is greater than 1, equilibrium prefers the products. Okay? We will generally have more products than reactants. All right, is what we're looking at there. All right? If the K is less than 1, the reaction prefers the reactants. Okay, that's all. It's not like which way, like I'm just saying, in the end, I'm not saying one is reacting more than the other. It's just at the end when you're in equilibrium, do you have more products or do you have more reactants? Again, the rates going back and forth are equal, but we might have an imbalance in terms of how much products you have versus reactants. Okay, so because it's a 7.1, this reaction does prefer the products a little bit more than the reactants. But like I said, you're going to get values which are like 1,000, and that basically means almost everything's turning into products, and you have very little reactants. You'll have values where are very small, and then that reaction hardly reacts at all before it comes to equilibrium. Okay, so don't forget about that too. All right, so here we go. Oh, I need to keep my number there. So K for the prior problem was 7.1, right? 7.1, that is correct. Okay. So this says some sulfur dioxide is removed from the reaction system. All right. If the value of Q is now 2.4, so Q equals 2.4, is the system in equilibrium? Well, does Q equal K? No, the system is not at equilibrium. Okay, it is not at equilibrium. But if it's not at equilibrium, which way will the system try to shift? I mean, you could answer this question based on what we already learned with Le Chatelier's principle. We're removing products, so which way does it want to go? But let's also prove the point. Q is less than K, which based on our notes, that means this is going to move toward products. We need to create more products to get Q to get closer again to K. All right, so that's what we're looking at with that particular part. All right. Let's try another one. I want to try another one down here. I found another one that I was interested in. Just so you see this. Okay. Oh, shoot. We're going to have to go all the way back a little bit. Sorry, I should have really looked over. I guess we'll go ahead and do this one. Let's try this one out. Okay. So, calculate the equilibrium constant for the following reaction. Again, if the equilibriums are blank, blank, blank. Okay. 0.5, 0.8, and 0.2. So we gotta make sure we're balanced. Two ends, the two ends. I now have 5 O's versus 6 O's, so guess what? I'm gonna have to double that. So now I have 4 ends, so 4 ends, 10 O's, 4, 8 plus 2 is 10. So we're gonna raise something to the 4th power here. That's gonna be pretty big. So for this one, my K is equal to the concentration of NO2 to the 4th power times O2 divided by N2O5 squared. So for this, we got NO2 is 0.8 to the 4th times 0.2 divided by 0.5 squared. That's a 5. Okay? And again, I'm using everything because there's no solids or liquids. So I need to do 0.8 to the 4th power times 0.2 divided by 0.5 squared. So I get an equilibrium constant of 0.33. Okay, 0.33 in the end there. All right. So I need to keep that because I was trying to do another problem lower. So let's keep on moving forward with that. There you go, 0.33. Okay. If the value, okay, I have K is equal to 0.33. Okay. If the value of Q is 0.35, is the system at equilibrium? We're close. We're very close. Again, I didn't round anything, and this should come out to 0.33. Okay, so we're very, very close, but we would say no, we're not. But this is not going to take very long to get to equilibrium. But now Q is greater than K, so we need to reduce the amount of products. So this is actually going to shift toward the reactants. We're going to shift toward the reactants. Okay? Because we need to lower that Q value. Some of it needs to turn back into reactants. All right? So let's keep going here. So I think there's one down here I was interested in. All right. In another trial reaction, after equilibrium is established, the amount of N2O5 is 0.66 moles and the amount of O2 is 0.24 moles. What is the equilibrium concentration of NO2 if the container is 2 liters? So there's a reason I wanted to do this. Okay? We said it at the beginning. I mean, this is another good one because we're having to go back and solve for one of the concentrations. All right? Which this one's actually pretty stinking tough. All right? But we're trying to find the concentrations of it. All right? Again, our K was 0.33. Okay? So with this, we need to make sure our values are in, again, molarity. And you can see that I'm given moles and liters. So I need to make sure I use the correct value, put them into molarity correctly. So if I do my equation, it would be 0.33 equals NO2 to the fourth. I'm not happy about this because I have to take to the basically root 4, okay? Then I would do 0.6, oh no, where is it? 0.24 divided by 2. The molarity is 0.24 divided by 2, which it would be 0.12. So you got it. You can't plug in 0.24, it's 0.12, and this would be 0.33 squared. Okay? So in this lovely equation we got, unfortunately, here, 0.33 times 0.33 squared. And then we would do divided by 0.12. And then we would take the root 4. So 4 root of that. And I'm getting that the concentration of NO2 would be 0.74 molar. Hopefully all my work is correct there. But that would be basically it. So I wanted to show that you do need to sometimes calculate out the molarity. We did 0.66 divided by 2 to get 0.33 molarity. We have to be in molar, so you do have to pay attention to the concentration, or sorry, the volume at times. All right? So that is equilibrium constant equations. We're looking again just to be able to write them out. Obviously be able to maybe solve for a particular value, the K, and then compare it with Q, and based on your Q and K, determine which way the reaction goes. We're going to end there, and I will finish up with one more video with ice charts separately. All right, thank you.